Hello, everyone in SCI6103, and thank you for coming to listen to my presentation. My name is Shania Channon, and today I'll be walking you through both my research topic and a personal passion of mine, which is light pollution. More specifically, we'll be addressing a more nuanced topic, which will be on the screen here, which is how do different wavelengths of artificial light in the visible and infrared spectrum contribute to sky glow and reduce the signal to noise ratio in ground based astronomical imaging. Now, it's quite a mouthful, but as an ecologist by trade and amateur astronomer by passion, I tend to be a little bit biased on this topic. However, light pollution is a highly relevant issue to almost every aspect of modern life, from astronomy to heritage, ecology, and public health. Artificial light at night is currently unfettered and pretty mismanaged. There's not a lot of policy around it, and many people don't even know that it's an issue in the first place. For astronomy in particular, we are rapidly losing our ability to read the stars and study the cosmos, which is a much loved pastime and science humans have indulged in for several thousand years. So, as humans, we fight against almost all calls and cycles of nature, and nighttime is no exception to this at all. We blast our night skies with neon, with billboards, streetlights, floodlights, advertising, you name it. We don't really know what harm we're causing when we do this. ALAN, or artificial light at night, is a silent but pervasive threat. Poorly designed lighting, like we can see here on the left-hand side, shoots light directly into the atmosphere, where it scatters and creates artificial sky glow. This disrupts many things, including us, but as Fulci states, ALAN fundamentally alters the way astronomers can observe the night sky, a problem which is actually bespoke to our current generation in the last 20 years. Now, you're probably wondering, what was that funny word, sky glow, that I used earlier? Well, sky glow is the term given to a diffuse and intense brightening in a dome-like shape that we tend to see over cities, but it can happen pretty much from any light source. Different wavelengths of light hit the atmosphere and they scatter, and they cause this illumination fallout, if you will, that can be seen from up to hundreds of kilometers away. This glow actually lowers the contrast between the dark night sky and the bright celestial objects like stars and planets. This sort of relationship is known as a signal to noise ratio, or SNR. And you might have noticed this actually yourself. If you've gone camping or out in the mountains, you'll notice that you can see the night sky a lot clearer out there because you are actually further away from the sky glow of the city. So if SNR, this relationship, is lowered too far, it is almost impossible to manually resolve fainter celestial objects, even with long exposure time and complex instrumental calibration, which, if you love stargazing as much as I do, presents a huge problem, as the ability to partake in even just amateur astronomy is slowly getting erased. Now, not all light is made the same. It turns out that wavelength of light actually really matters when it comes to this issue. Rayleigh scattering is the process of light scattering in a medium, a small medium, so kind of like water vapor, and its efficiency is largely dependent on wavelength. This process is mostly responsible for why we see a blue sky during the day. The intensity of this scattering, as stated by Lamphar on the screen here, is inversely proportional to the fourth power of wavelength, which is another mouthful, and it's a very fancy mathematical way of saying that blue light, as you can see on the graph here, at approximately 400 nanometers, scatters around 10 times more efficiently than redder visible infrared light, closer to the 700 nanometer mark. Now, there is another type of scattering in our atmosphere when it comes to light pollution. Rayleigh, as we just covered, is scattered by molecules smaller than the wavelength of light and is highly dependent on wavelength. But we also have Mie scattering, which is perpetuated by larger particles in our atmosphere, like aerosols. Mie scattering is responsible for a smaller portion of the atmosphere scatter. It's not the most. Rayleigh is definitely the most. And it's a little bit more resilient to wavelength type as well. Though it is worth noting that short wavelengths, so our blue light, 400 nanometers, does still scatter more efficiently with Mie scattering as well as Rayleigh. So all of that to say that even a small amount of blue light in the atmosphere will scatter far more dramatically than a large amount of red light will. So that kind of gives you a hint of why this problem is a little bit exponential. And the past few decades, we've turned away from our higher wavelength, beautiful orange incandescent lighting that we can see on the screen here in our halogen lamps. They emit around the 700 nanometer mark. They have a peak in their light curve around there. And we've made this really swift, sharp turn into white, bright LEDs. And they emit significant amounts of blue light, 400 nanometers. So if you look at their light curve, they have this huge peak at the blue. And they are absolutely everywhere. They are on billboards, advertising, downlights, our computer screens, our phone screens, torches, headlamps, you name it. Everything is now LED. A case study from this year actually showed that even just a small but concentrated amount of blue light in the atmosphere can be observed up to 5 kilometers away in a dark night sky setting. And with our sky glow domes of our cities, they extend like several hundred of kilometers. So what effect does that actually have on astronomy? Well, ground-based astronomy, so our big, beautiful observatories on the ground, is hugely dependent on that signal-to-noise ratio that we discussed earlier. The darker the sky, the more contrast there is between the sky, the background, cosmos, and the targets that we observe, so our stars and planets. As sky glow increases, it completely washes out the contrast, like you can see on the screen here. And observatories are forced to perform either long exposure analysis or extensive calibration and filtering to sort of mitigate that sky glow. Both of these mitigation options are taxing on both time and finances, and a lot of observatories can't actually afford to make those observations anymore and those calibrations. So some faint targets can't be resolved altogether, even with those processes. So there is a large portion of stars and planets that we just simply can't observe anymore because of light pollution. There have been some recent advancements in mitigation, such as narrowband filtering. However, light pollution is increasing at a rate of around 10% annually across the globe. And majority of that LED-based lighting will soon come a time where ground-based observatories simply just cannot filter out the noise. There are missions like Gaia and TESS, which are space-based telescopes, and they are long-term telescope missions. And they're increasingly more popular for astronomy research as they operate outside of Earth's atmosphere and they get to skip the light pollution altogether. But as you can imagine, extremely financial burden to launch those missions. So what can we do? Well, there are several initiatives across the world, but there's one in particular, which is ADSA here in Australia, that are committed to making better lighting choices, and they advocate for light pollution to be an issue of the past. They do amazing work. They host seminars and conferences if you're interested. We do actually have the technology to shift to warmer spectrum efficient lights designed in a way that can protect our night sky. And we just simply need to be more conscious and move towards that. So in summary, blue-rich light scatters in our atmosphere at an exponential rate. And the switch to LED lighting is good for our electricity bill, but it's quickly pushing amateur and research astronomy to, frankly, extinction by lowering that SNR, or lowering that contrast. The costs to losing our night skies are significant for culture, heritage, science, biodiversity, even public health. Through smarter lighting choices, education, and stronger policy regulation, it is possible to protect our stars. Thank you so much for listening. And if you are more interested in finding out a little bit more about ADSA in particular and light pollution, I am a committee member and would love to have you reach out and we can discuss more. Thank you so much for listening. I hope you found this informative and enjoyed. Here are my references. Thank you.